Water and hydrogen. Water is the most abundant substance constituting about 1% coverage of the Earth's surface. Water is found free in water bodies such as oceans as well as component of the living system, all incorporated in various compounds and mixtures. We look at reactions of water and we'll start with the reaction with metals. When a piece of sodium metal is placed in water, it reacts vigorously, darting on the surface and producing a hissing sound. A colorless gas is, and the solution that remains after the metal has melted is basic or alkaline. The colorless gas is hydrogen. Take a look at this. The reaction that occurs can be represented by the following equation: sodium plus water to form sodium hydroxide, which is the alkaline, plus hydrogen gas. When calcium is put in water, it reacts, producing a stream of bubbles. If the gas produced is tested with a burning splint, it burns with a pop sound. This gas is hydrogen. A white suspension is formed because calcium hydroxide formed is slightly soluble in water. A base that is soluble in water is called an alkali. Take a look at this. The reaction that occurs can be summarized by the equation on your screen: calcium reacting with water to form calcium hydroxide plus hydrogen gas. Generally, water reacts with metals to form metal hydroxide and hydrogen gas. Magnesium reacts very slowly with water, while zinc, iron, and copper do not react at all. The reaction of potassium with water is an explosive one. The potassium metal, when placed in water, melts into a silvery ball, moving about rapidly on the surface and generates a lot of heat. Hydrogen gas is produced and ignites spontaneously because of the heat. The flame produced is lilac due to the presence of potassium vapor produced during the reaction. Take a look at this.
Wow.
That reaction can be summarized by the following equation: potassium reacting with water to form potassium hydroxide and hydrogen gas. Now let's look at reaction of metals with steam, and we shall look at magnesium and steam. Some metals do not react with cold water but can react with steam. When steam is passed over heated magnesium metal, it burns brightly in the steam, forming white magnesium oxide powder and hydrogen gas. Take a look at this. We have the magnesium ribbon in the test tube or the boiling tube, and then at the bottom we have wet sand. Now we are going to heat the magnesium ribbon until it glows. We are going to heat the magnesium ribbon. Once it is hot, we will heat the sand to generate steam. When the two react, we shall see what happens. Take a look. So there you have the magnesium ribbon burning brightly in the steam to form magnesium oxide, and at the other end you can see hydrogen that is produced burns quietly. The other end we have hydrogen burning. Zinc and iron glow in steam but never burn. Zinc reacts with steam, forming a yellow powder of zinc oxide which turns white on cooling. That reaction is summarized by the equation zinc plus steam to form zinc oxide and hydrogen. Iron forms a black residue of an oxide of iron called triiron tetraoxide. That is also summarized by that equation. Lead and copper do not react with water nor steam. Aluminium reacts with steam, but the reaction stops after some time due to formation of a coat by aluminium oxide, which prevents further reaction. Accordingly, we can have the reactivity series of metals with steam as follows, from the most reactive to the least reactive. And now we look at hydrogen, and hydrogen is the simplest and lightest element. It does not exist as a free element but exists combined in forms such as water, hydrocarbons, hydroxides, and so on. In gaseous form, two atoms combine to form a hydrogen molecule. How is hydrogen gas prepared in the laboratory? We have already seen that the reactions of metals with acids and water generate hydrogen as one of the products. Now you already know how hydrogen can be prepared. In labs, we prepare hydrogen by reacting a metal and an acid. Zinc is the most suitable for this purpose. The reaction is illustrated on your screen next. There we have the setup for preparation of hydrogen gas. So at the bottom there we have zinc granules. Zinc granules at the bottom there, and then we have hydrochloric acid, which we are going to react with zinc granules to generate hydrogen. The gas will be collected over water because it is insoluble in water. So we add the acid through the Wistar funnel, and the reaction generates hydrogen gas, which passes through the delivery tube into the gas jar and displaces the water downwards. There we have our hydrogen gas. This reaction can be speeded up by adding small amounts of copper to sulfate as a catalyst. Potassium, sodium, and lithium cannot be used in place of zinc. Why? Because their reactions with acids are explosive. Magnesium can be used, but it is expensive. Zinc is preferred because it reacts moderately with dilute acids. Impure iron produces a mixture of gases including the awfully smelling hydrogen sulfide. Nitric acid is not used because hydrogen formed is oxidized to water, but very dilute nitric acid can generate hydrogen with magnesium. Hydrogen is a colorless gas that is insoluble in water, and so it is collected over water. It is, however, less dense than air and is collected by upward delivery. This method is also called the downward displacement of water. The gas is delivered upwards, water is displaced downwards. Hydrogen gas burns in air with a pop sound, but pure hydrogen burns quietly.
Okay. Okay. Ready? 3, 2, 1. Okay. Okay. Ready? 3, 2, 1.
Let's look at reduction properties of hydrogen. And we start with passing hydrogen over hot copper 2 oxide. When a stream of hydrogen gas is passed over heated copper 2 oxide, the black solid turns red-brown and a colorless liquid condenses at the cooler parts of the combustion tube. Take a look at this. So there you have copper 2 oxide, and when heated, and then hydrogen gas is passed over the heated copper 2 oxide, you will realize that we have a red-brown solid that is formed, that is copper metal, and then a drop of water can be seen at the cooler parts of the apparatus. Hydrogen combines with oxygen in copper 2 oxide to form water, that is the colorless liquid. The red-brown solid is copper. The removal of oxygen from a compound is called reduction, while the addition of oxygen is called oxidation. In this reaction, we say copper 2 oxide has been reduced to copper, while hydrogen has been oxidized to water. The reaction can be represented by the equation on your screen. Copper 2 oxide plus hydrogen becomes copper plus water. Hydrogen is therefore a reducing agent, while copper 2 oxide is an oxidizing agent. Hydrogen can also remove oxygen from oxides of lead and iron. That is, lead 2 oxide plus hydrogen will form lead and water. Iron 3 oxide plus hydrogen will form iron and water. However, hydrogen cannot reduce the oxides of more reactive metals like potassium and sodium. When a burning splint is lowered into a tube containing hydrogen, a pop sound is produced, and this is the test for hydrogen. We say a mixture of hydrogen and air burns with a pop sound. However, pure hydrogen burns quietly in air to form water. That is, hydrogen plus oxygen gives water. Finally, we look at the uses of hydrogen. And hydrogen is used in the Haber process in the large-scale production of ammonia. It's also used in hydrogenation, that is hardening of oils in the presence of nickel catalyst. It is used in air balloons. Why? Because it is lighter than air and therefore it rises. It is used in welding and cutting of metals when mixed with oxygen. It is also used as a rocket fuel. Also used in the manufacture of hydrochloric acid, and it is also used as fuel in fuel cells.
You can always spot the brightest minds, the ones who think bigger, who push concepts a little further. When you combine theory with practical study, you get university students that are more switched on. That's why Curtin graduates are ready to make a difference from day one, to help make tomorrow a better place.